Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Absolutely. It really helps out.
Yeah, so imagine dropping a plugged-in hairdryer into a bathtub. You basically have a fraction of a millisecond before, a lethal amount of current finds a path right through human heart to the ground.
Right. Which is obviously a terrifying thought.
Exactly. But the only thing preventing a fatality there isn't some complex microchip or like a smart computer algorithm. It's literally just a fundamental law of physics reacting to invisible electromagnetic fields.
Yeah, fields that are just operating in the empty space right around the wires inside your walls.
It's wild. So today's deep dive is basically a masterclass in electromechanical systems. We are answering the biggest questions engineers ask online about how energy is actually stored, how it turns into physical motion.
And, well, how we predict the dynamic response of those physical systems, because that's the hard part.
Right. So you are sitting at your personal workbench today, and we are going to connect this completely invisible world of electromagnetic fields directly to the tangible world of moving masses and springs.
Which is something that is, frankly, misunderstood by a lot of working professionals. I mean, for decades, mechanical engineering and electrical engineering have been taught as, like, totally isolated disciplines.
Yeah, you take your Newtonian dynamics classes in one building, right?
Dealing with inertia and friction and steel.
Exactly. And then you walk across campus to take your electrodynamics classes where it's all Maxwell's equations and, propagating waves.
But nature doesn't care about that academic divide, does it?
No, not at all. When you design a modern actuator or an EV powertrain or even a microscopic optical switch, those two domains just violently collide.
You really have to realize that mechanics and electromagnetics are governed by the exact same physical constraints.
They absolutely are. So before we can actuate anything, move any physical mass, we need source of energy. And right now, there's this relentless push toward electrifying literally everything.
Oh, yeah. Vehicles, industrial heating, aerospace, everything.
But when you actually look at the raw data, there's a huge discrepancy. Like, liquid fossil fuel still holds a staggering advantage in energy density.
It really does. It's almost hard to comprehend until you look at the numbers.
Right, because one single gallon of gasoline yields roughly 40 kilowatt hours of energy, and it only weighs 2.75 kilograms.
Yeah, and then compare that to early mass-market electrification. Look at an older Toyota Prius, right? The nickel-metal hydride battery pack.
Oh man, the numbers on that are rough.
They are sobering. That entire pack yields only 1.8 kilowatt hours of energy, but it weighs 52 kilograms.
Wait, 52 kilos for 1.8 kilowatt hours?
Yeah. So you're getting a tiny fraction of the total energy, but you're hauling around this massive amount of physical weight.
So if gasoline provides like over 20 times the energy while weighing practically nothing by comparison, why are engineers so obsessed with tearing out combustion engines?
Well, it comes down to...
Like, why accept that massive penalty in weight and volumetric efficiency? What's the physical constraint making electrical storage so heavy?
So it's really about where and how the energy lives at the atomic level. I mean, gasoline is a chemical energy store. The power literally comes from breaking molecular bonds.
Like breaking the carbon and hydrogen chains.
Exactly. You're oxidizing them. So almost 100% of the mass of that liquid is active, combustible material just waiting to release energy.
Right. And the only containment you need is just like a cheap plastic or stamped metal tank.
Which doesn't do anything but hold the liquid, right?
Yeah.
It's just a bucket. But electrical storage is entirely different. Let's look at capacitors and inductors, the direct ways we store electrical energy.
Okay, so a capacitor stores energy in the electric field between two plates.
Right. And an inductor stores it in the magnetic field generated by current in a coil. But here's the fundamental problem. The universe places very strict physical limits on how much energy you can cram into a field.
Because things break, right.
Yeah.
If you crank the voltage too high across a capacitor, the electric field gets so intense it just rips electrons away from the molecules.
Exactly. The dielectric material fails. You get a catastrophic spark, a dielectric breakdown.
So what are the actual limits then?
Well, for a magnetic field, the maximum energy density you can safely maintain before the iron core just completely saturates is roughly 400 kilojoules per cubic meter.
Okay, 400 kilojoules. What about electric fields?
For macro-scale electric fields, because of that dielectric breakdown we just talked about, it maxes out around 4.4 joules per cubic meter.
4.4 joules, not kilojoules, just joules.
Joules.
Wow. But gasoline sits at, what, 38 gigajoules per cubic meter?
38 gigajoules, yes. It's an astronomical difference. Gasoline holds billions of times more energy in the same physical space than an electric field ever could.
That's insane. And I guess on top of those fuel limits, electrical systems just carry so much dead weight.
Oh, tons of it. To use a battery, you need thick metal plates for the anode and cathode,
Yeah.
heavy structural casings to safely hold the reactive electrolytes.
Dielectric separators,
Ugh.
thermal management so it doesn't just burst into flames.
Right, all that copper and steel and coolant, it adds massive weight, but it contributes literally zero motive energy. It's just packaging.
So it's basically like hauling around a giant, heavy steel safe just to transport a very tiny spring inside it.
Yeah.
While gasoline is just, a weightless spring.
That's a perfect analogy, yeah.
But then, back to my main question. If liquid fuel is so vastly superior, why do we prioritize electromagnetic fields in modern design?
Because of one crucial word, control. Yeah. Extracting energy from gasoline requires a violent, chaotic explosion. Internal combustion is just naturally sluggish. You have valves, camshafts, heavy iron pistons that take time to spool up.
Right, you can't exactly throttle an explosion down to the minus
Yeah, well,
nine.
you can't unexplode fuel, but electromagnetic fields, we can manipulate an E or H field in fractions of a millisecond. We can shape it, pulse it, reverse polarity almost instantly.
Oh, so we are intentionally trading that raw, brute force energy density just to get the surgical precision of a field.
Exactly, because high-speed robotics, precise industrial automation, microscopic medical devices, none of that works with combustion. You need instantaneous feedback loops.
Yeah, makes total sense. Okay, so since we rely on these fields for precision, how do we mathematically and practically turn that invisible field into actual mechanical force?
Well, there is a universal rule for predicting this, and it saves engineers from doing pages of agonizing vector calculus. It's called the energy method.
The energy method.
Oh.
Okay, how does it work?
The golden rule is that forces in any electromechanical system will always act in a direction that minimizes the total stored energy of that system.
So the system is lazy.
Yeah.
It just wants to reach the lowest possible energy state.
Right, like a stretched rubber band wanting to snap back.
Yeah.
Practically, this gives you two clear rules. In an electrostatic system, the force will always act to increase the capacitance.
Increase the capacitance, okay.
And in a magnetostatic system, the force will always act to increase the inductance.
So to avoid textbook math, if I'm designing a linear actuator, like a solenoid, the force pulling the plunger isn't just about the voltage.
No, it's about the rate of change. The force on that plunger is 1/2 times the current squared, multiplied by the derivative of inductance with respect to position.
So if the object moves but the inductance doesn't change at all, there's zero magnetic force.
Exactly. You need a steep change in inductance relative to position to get a violent physical pull.
And we see this in variable reluctance motors, right?
Yeah.
The rotor is machined with these jagged iron teeth, sort of like a gear.
Yeah, and the stationary housing around it, the stator, has matching iron teeth wrapped in heavy copper wire.
So when you pulse current through those coils, a magnetic field forms across the air gap.
And the system hates that air gap because air has terrible magnetic permeability. It's storing immense energy just trying to push flux through the air.
Right, so to minimize its energy, it wants to maximize its inductance.
Yeah.
It physically pulls the rotor's iron teeth into direct alignment with the stator teeth.
Because the iron provides an easier path for the magnetic flux. Once they align, the air gap is gone, inductance peaks, and the system hits its lowest energy state.
And then the controller just cuts the power to that coil and turns on the next one, dragging it into continuous rotation. It's literally a carrot on a stick.
Exactly.
Okay, what about the electrostatic side? You said force acts to increase capacitance.
So look at microscopic silicon mechanisms, MEMS devices, micro-electromechanical systems.
Like the tiny mirrors and high-end digital projectors.
Yeah. You can't wind copper wire at the micrometer scale, so they rely on electrostatic actuation. A common one is the linear comb drive.
Right, so imagine two microscopic combs. The teeth of one are interlaced to the teeth of the other, but there's a tiny air gap, so they aren't touching.
When you apply a voltage, an electric field forms across those gaps. The system wants to minimize its stored energy by increasing its capacitance.
And capacitance is based on overlapping surface area.
Exactly. So the electrostatic force literally pulls the moving comb deeper into the stationary one, sliding the teeth past each other to increase the overlap.
That's brilliant. I want to bring up this household example too because it perfectly illustrates this. Refrigerator magnets. magnetic poetry.
Oh yeah, fridge magnets operate on a fascinating manipulation of the flux path.
Because they aren't just normal bar magnets with a north pole on one end and a south pole on the other, right?
No, not at all. They're made by embedding strontium ferrite particles into a rubber binder, and they magnetize them so the poles are in alternating parallel stripes right on the back surface.
So it's like north, south, packed super close together.
Right. And because they're adjacent on a flat surface, the magnetic field lines don't project out into the room. They arc tightly from a north stripe, loop over, and dive straight back into the neighboring south stripe.
So when you bring that near a steel fridge door, the energy method takes over. The flux hates the air. It wants the low reluctance path of the steel.
Yep. To minimize stored energy, it pulls the rubber sheet violently flat against the steel door. It collapses the air gap, maximizing the inductance of its local magnetic circuit.
Okay, let's unpack this for a second, though, because there's a paradox here.
There is, and it trips up a lot of engineers.
Yeah, you're saying the system is lazy, it wants to lower its overall stored energy, but the rules explicitly say the mechanical force acts to increase the capacitance or inductance.
Right.
If the capacity to store energy goes up, like making a bucket larger to hold more water, how does the system's total energy actually go down?
It comes down to understanding what variable is held constant during the movement. Let's isolate that cone drive capacitor. The total energy stored is 1/2 multiplied by the square of the electrical charge divided by the capacitance.
Okay, the charge squared divided by the capacitance. So the capacitance is in the denominator.
Yes. So if you charge the cone drive with a battery, then disconnect the battery, the electrical charge is trapped, the electrons have nowhere to go, the charge is perfectly constant.
Right.
Now the electrostatic force pulls the teeth together, the overlapping area grows, so the capacitance gets larger.
And mathematically, if the denominator gets larger while the numerator stays the same, the total fraction drops.
Exactly. By increasing its capacitance under a constant charge, the system is actively bleeding off its stored electrical energy. It converts that potential directly into the physical work of moving the cone.
It's a beautiful mathematical paradox.
Yeah.
The field basically collapses its own energy to perform physical work.
It perfectly dictates all electric motor design.
That transitions perfectly into the next huge question. If an actuator converts electrical power into physical force, how did the power physically travel from the battery to the actuator in the first place?
This is where we have to unlearn what they teach in high school.
Right, because we are all taught that power flows through the wires,
Yeah.
carried by the electrons, like water in a pipe.
Which is fundamentally incorrect. If you want to know how power truly travels, you look at Poynting's theorem. John Henry Poynting and Oliver Heaviside derived it from Maxwell's equations.
Okay, and what does the theorem actually say?
The power density is the cross product of the electric field and the magnetic field, E cross H.
So a vector cross product gives you a third vector that is perpendicular to the first two. If the electric field points up and the magnetic field points right, the power flows straight forward.
Exactly. And here is the mind-blowing fact. The energy does not flow inside the metal wires.
Wait, really? The energy isn't in the wire?
Not at all. In alternating current, the electrons are barely moving down the wire. Their drift velocity is like fractions of a millimeter per second. They just oscillate in place.
So the wires don't carry the energy.
They merely guide the fields. They act as physical boundary conditions. The actual usable energy flows through the empty space around the wires.
So the wires are just the riverbanks, but the electromagnetic field outside the copper is the actual river doing all the pushing.
Yes. The voltage differential creates an electric field in the space between the wires. The current generates a magnetic field wrapping around them. A changing E field creates a changing H field, and they lock together.
And they just propagate through the space around the cable.
Right, at a significant fraction of the speed of light. And when those fields reach the motor, they dive into the load and transfer their energy to do the work.
Okay, push back on this. If the power is entirely outside the wire, why do extension cords get hot? Doesn't Joule's law say power is dissipated inside the conductor?
I love this question. The heating is actually a direct result of that exact cross-product math.
How so?
In an ideal universe, with perfectly conductive wires, the electric field lines are perfectly perpendicular to the surface of the wire. When you take the cross product, the resulting Poynting vector points perfectly parallel to the wire.
So the energy glides straight down the outside undisturbed.
Exactly. But copper isn't perfect. It has resistance. That creates a slight voltage drop down the length of the wire.
Meaning the electric field is no longer perfectly perpendicular, it tilts.
It tilts slightly forward, so when you recalculate the cross product with that tilted electric field, the power vector also tilts. It's no longer perfectly parallel. A tiny fraction of that vector now points directly into the surface of the wire.
Oh, wow. The field physically crashes into the metal.
Yes, it penetrates the copper and dissipates as heat because it's colliding with the atomic lattice. That is Joule heating. The wire gets hot because the pointing vector points into it.
But the vast majority of the vector still points forward, delivering the useful work to the motor. That is wild. And engineers actually use this understanding of field dynamics to save lives. The ground fault interrupter, the GFI outlet in your bathroom, operates entirely on this physics, right?
It does. A GFI is a brilliant application of a differential transformer. Inside the outlet, the hot wire bringing power in and the neutral wire returning it are both passed through the center of a single magnetic core, like a donut.
So both the supply and return rivers flow through the exact same sensor.
Right. Normally, the current flowing in is perfectly equal to the current flowing out. The hot wire makes a clockwise magnetic field. The neutral makes a counterclockwise one.
Because they're equal and opposite, the magnetic flux inside the donut perfectly cancels out to zero.
Net magnetic field of zero. So the secondary coil wrapped around that donut sees absolutely nothing.
But if a fault occurs, say that hairdryer falls in the tub and current finds a path to ground through a person, the hot wire has, say, 10 amps in, but the neutral only has 9.9 returning.
The symmetry breaks. The fields no longer cancel out. Instantly, a net magnetic flux materializes in the donut. And because it's AC, it's varying in time.
Which means Faraday's law of induction kicks in.
Instantly. The changing flux induces a voltage in the secondary coil, which fires a small solenoid to unlatch the contacts and break the circuit.
In just milliseconds.
Way faster than a thermal breaker could ever react. All because it's monitoring the actual invisible fields instead of heat.
That's incredible. And we manage these fields even without wires, right? Like with propagating waves in radar. The source material talks about radomes, those giant golf ball domes protecting radar antennas.
Oh, radomes are a perfect example of managing boundary conditions. When a radar wave hits the fiberglass wall of the dome, the impedance mismatch causes part of the wave to reflect back toward the source and the rest transmits through.
But if you're listening for faint echoes from an aircraft, a massive reflection from your own dome bouncing right back into the receiver is disastrous.
Right, you want 100% transmission. But you can't stop the physics of reflection at a boundary.
So how do they fix it?
They use wave interference. They make the physical thickness of the fiberglass exactly 1/2 wavelength of the radar's operating frequency.
Okay, so the wave hits the inside surface. A reflection bounces back. The rest travels through the solid wall, hits the outside air boundary, and a second reflection bounces back.
Now you have 2 echoes. But that second echo traveled a 1/2 wavelength forward through the wall and a 1/2 wavelength back. It traveled 1 full extra wavelength.
Right.
And because it transitioned from dense fiberglass to lighter air, a phase inversion occurs at that outer boundary.
The wave flips upside down.
Yes. So when that second inverted reflection meets the first one at the inner wall, the peaks of one align perfectly with the troughs of the other.
They destructively interfere and annihilate each other.
And since the energy can't just vanish, conservation of energy forces 100% of the radar's power to transmit cleanly through the wall into the open air.
It uses the wave's own reflections to destroy the reflection. That is elegant.
It really is.
Okay, so we've got the energy limits, we've got the power flow, and the force generation. Now, the actuator responds, and the mechanical object actually begins to move. How do we build mathematical models to predict exactly how a mechanism will respond to an input force over time?
This brings us into system dynamics, specifically linear, time-invariant systems, or LTI systems.
Right. Because a mass rarely snaps instantly to its final position. It has to fight inertia and friction.
Exactly. We classify the system's order by the highest mathematical derivative in the equations. Let's start with a first-order system.
So a first-order system is just a mass and a damper. Inertia and viscous resistance, no spring.
Right. Think of a reaction wheel inside a spacecraft. You apply a constant stepped torque from an electric motor. The wheel doesn't instantly hit max speed. The mass resists acceleration, and the bearing friction dampens it.
So if you graph the velocity, it curves exponentially toward the max speed.
It forms an asymptotic curve, yes. And we define the sluggishness of that curve with a metric called the time constant, represented by the Greek letter tau.
Which is just the mass divided by the damping coefficient, right?
Yep, it guarantees how the system behaves. After exactly one time constant, the wheel will reach roughly 63% of its final speed. After 3 or 4 time constants, it's essentially at steady state.
We see that with an airplane rolling, too. Ailerons actuate, but the plane doesn't instantly roll at 40 degrees per second. Inertia and drag delay it, following that exact same first-order exponential curve.
Very predictable, smooth slide. But if you add a spring, you allow the system to store potential energy. Now you've elevated the math to a second-order system, a mass, a damper, and a spring.
And the mass stores kinetic energy, the spring stores potential energy, and they can continuously pass it back and forth.
Which is the fundamental source of all mechanical vibration. To predict this, you need 2 parameters, the natural frequency and the damping ratio.
Natural frequency is how fast it naturally oscillates, and damping ratio is how fast the friction leads off the energy.
Exactly. And the damping ratio, called zeta, determines which of 3 states the system falls into. First is underdamped, where the ratio is less than 1.
So the friction is low. You hit it, it shoots past the target, the spring pulls it back, it shoots past again, and just keeps oscillating until it slowly settles.
Like a car driving over a pothole with blown shock absorbers, it just keeps bouncing.
And if the damping is massive,
It's overdamped. The damping ratio is greater than 1. The friction is so dominant the mass never overshoots. It sluggishly crawls to the target without a single oscillation.
like trying to slam a heavy vault door shut when the hinges are packed with thick tar.
Perfect example. And then there's a third state, the purely theoretical one, undamped. A damping ratio of exactly 0, no friction, no air resistance. The mass just bounces forever.
Okay, here's where it gets interesting, though. Friction is literally everywhere. Energy is always lost. Why do engineers even bother teaching undamped systems? Isn't it just a theoretical fairy tale?
You'd think so, but the undamped natural frequency is the fundamental baseline. It is the system's DNA. It's a pure ratio of spring stiffness to mass magnitude.
Oh, so the real-world friction just obscures the true behavior.
Yes. You can't understand how a physical structure will respond to a massive wind load without stripping away the friction to uncover that underlying DNA.
But how do you mathematically measure something without friction in the real world?
Engineers use what's called a twang test.
A twang test.
Yeah. Imagine characterizing a large antenna boom on a rover. You pull the tip back a few inches and let go. You twang it like a guitar string. Sensors record the vibration.
But they're recording the damped frequency because the metal's internal friction is fighting the oscillation.
Right. You look at the sine wave, and the peaks are visibly getting lower with each cycle. By measuring the amplitude decay from one peak to another several cycles later, they calculate the logarithmic decrement.
Which gives you the exact damping ratio.
Exactly. Once you know the real-world friction and the damped frequency, you apply a simple algebraic transformation to mathematically erase the friction. It reveals the pure, undamped natural frequency.
So you use the messy reality to reverse engineer the pure theoretical DNA. That's awesome.
It really is.
Okay, so we've looked at mechanical responses, but here's the ultimate shortcut for an engineer. Mechanical and electrical systems use the exact same math.
The principle of mathematical duality. It is arguably the most powerful conceptual shortcut in engineering.
Let's trace it. If an engineer wants to solve a mechanical dynamic problem, how do they use circuit theory?
If you write out the second-order differential equation for a mass suspended by a spring and a shock absorber, and then write the equation for an electrical circuit with a resistor, an inductor, and a capacitor.
They're exactly the same.
Mathematically identical. Only the letters representing the physical properties change.
Okay, let's walk through the physical equivalents. We know mechanical force initiates movement. What's the electrical equivalent?
Voltage. Force pushes a mass. Voltage pushes a charge.
And the physical velocity of the mass moving through space.
That translates directly to current. Current is the velocity of the electric charge flowing past a point.
Okay, the mechanical damper provides viscous friction, converting kinetic energy into heat.
The damper is the resistor. It restricts current, causing collisions that dissipate electrical energy as heat.
The mechanical spring stores potential energy as it's stretched.
The spring is the capacitor. It stores electrical potential energy based on the physical separation of charge across its plates.
And finally, the heavy mass, which resists any sudden change in velocity due to inertia.
That perfectly mirrors the inductor. It stores kinetic energy in a magnetic field.
Yeah.
It violently resists any sudden change to the current flowing through it. It acts as pure electrical inertia.
So if I build a series ROC circuit resistor, inductor, capacitor in a loop, I've basically constructed an analog computer that perfectly simulates a mass damper spring system.
Flawlessly. And the behaviors are identical, especially with frequency response.
Right. If you hit a mechanical system with an oscillating force at its natural frequency, it enters resonance. It absorbs energy until it tears itself apart, like the Tacoma Narrows Bridge swaying in the wind until it collapsed.
Mechanical resonance is almost always catastrophic. But in the electrical domain, resonance is incredibly useful.
Wait, how so?
When you hit an RLC circuit with an alternating voltage wave that perfectly matches its natural electrical frequency, the total impedance drops to its absolute minimum.
And so the signal rushes through with maximum amplitude while all other frequencies are blocked.
You've constructed a perfect bandpass filter. That is the fundamental physics of a radio receiver.
Oh, wow. So when you turn the dial on an analog radio,
You are physically changing the capacitance of a variable capacitor. You are tuning the electrical natural frequency until it perfectly matches the invisible radio wave you want to listen to.
the circuit resonates with that specific wave, ignoring everything else.
Exactly.
So if I'm designing like a specialized active mass damper to stop a skyscraper from swaying in the wind, I don't need to reinvent the wheel.
Not at all.
I can literally just sketch out a basic RLC electrical circuit, run the math, and I have my mechanical blueprint.
Absolutely. Whether you are tuning an active mass damper for a building or tuning a radio receiver, you are manipulating the exact same differential equations. Master the math once, and you master both disciplines.
The calculus simply does not care what the physical medium is.
It's blind to it.
That is stunning. Okay, so we've tracked energy density, the flow of power through empty space, the math of masses and springs. Let's close out this workbench session with a final provocative thought from our sources. Terahertz lasers, or T-rays.
Ah, yes. Taking these macro-scale principles down to the subatomic level, terahertz radiation sits between microwave and infrared.
And there's huge funding for it right now, right? Because T-rays can pass right through clothing and plastic like glass, but they bounce off water and solid metals.
Exactly. They are perfect for scanning for concealed metallic objects without using harmful ionizing X-rays.
But why does that specific frequency ignore the plastic but bounce off the metal?
It relies entirely on the system dynamics and resonance we just talked about, but scaled down to the electron level.
How does that work?
In a metal, the outer electrons form a free-flowing sea. We can mathematically treat them as a massive group of tiny microscopic harmonic oscillators.
So they're basically infinitesimal masses attached to the restorative spring force of the atomic lattice.
Yes, we are treating subatomic particles exactly like the mass damper spring system of the skyscraper.
That's crazy.
And because the electrons are so incredibly light and the spring force is so strong, their natural frequency, the plasma frequency, is phenomenally high, up in the petahertz range, quadrillions of cycles per second.
So the electrons naturally want to vibrate incredibly fast, but the T-ray is in the terahertz range.
Which is roughly 1,000 times slower. The driving sinusoidal force of the T-ray is moving much, much slower than the speed at which the electrons naturally want to vibrate.
So the electrons have plenty of time to dynamically respond.
Exactly. As the T-ray's electric field pushes, the sea of electrons shifts instantly, generating an opposing electric field that perfectly cancels out the incoming wave. They act as an impenetrable mirror.
Because their subatomic inertia is so low. But what about the plastic?
In plastics, the electrons are tightly bound in covalent bonds. They act like masses attached to incredibly stiff, rigid springs, heavy internal damping.
So when the T-ray hits them, they're too restricted to shift and generate an opposing field.
They cannot react, so the electromagnetic wave just propagates straight through the empty space of the atomic structure, completely ignoring the material.
The exact same macroscopic mathematical framework that governs a variable reluctance motor and a skyscraper damper perfectly dictates how a beam of invisible light interacts with the subatomic particles of the universe.
The universe is just fields and oscillators.
Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.